Hello everyone, this is Mo Hasanovic with Indian River State College and LASER-TEC, Advanced Technological Center of Excellence in Lasers and Fiber Optics Education, a center supported by National Science Foundation. The title of this lab number 12 is Measuring the Focal Length of a Biconvex Lens. Double convex or biconvex lens is an important optical component. It has the shape of a lentil with two surfaces pointing outwards, meaning that the center of the lens is thicker than the edges. This is an important optical component that's being used in many different applications as a magnifier, such as cameras, projectors, telescopes, etc. And it's also being used to correct human vision, specifically so-called hyperopia or farsightedness. A lens in general represents an optical device that's made out of transparent material, has a focusing ability. An important property of a lens is so-called focal point, and that is the point where all parallel rays that are passing through the lens are being focused. The distance from the focal point to the lens is so-called focal length. So the purpose of this lab is to learn a little bit about the biconvex lens and to set an experiment in which we are going to determine a focal length of an unknown biconvex lens. The learning outcomes for this lab is to define the biconvex lens and its major characteristics, to set up an experiment, measure and record the relevant data, specifically the focal length of an unknown lens. We are going also to learn how to perform the tracing of light rays emitted by an infinite source and traveling through a biconvex lens. As already mentioned, we are going to measure the focal length of this type of a lens and finally list common applications of this important optical component. The equipment for this lab consists of a flashlight to be used as a light source, flashlight holder, biconvex lens, a lens holder, measuring tape, and finally a pencil and white sheet of paper. I have positioned the measuring tape here along the longer line of the white sheet of paper. I put the back screen in the back here and positioned the back screen exactly at 0 of my measuring tape, and then in front of the back screen I positioned the lens in the lens holder. The flashlight has been placed in the back here at about 50 to 90 centimeters away from the back screen. It's important to emphasize that for this lab to be successful, your laser has to be positioned at least 50 and preferably 80 to 90 centimeters away from the screen. The reason for that is, farther you put the laser away from the screen, the direction of the light rays that are coming out of the flashlight is going to be more parallel, and that's an important condition for this experiment to be successful. So we want to have light ray hitting lens from a parallel directions, which is basically good replica of a source that's being positioned at an infinite distance. So again, you would want to position the laser at least 50 centimeters, preferably 80 to 90 centimeters away from the screen and from the lens to fulfill the condition of parallel direction of the light rays that are hitting the lens. So now if you start moving this lens in a lens holder back and forth along your measuring tape, what you're going to realize that at a certain position away from the screen, you're going to start seeing an image of 6 small LEDs that are part of your flashlight. You can see them here. And if you continue moving closer, the sharpness of that image is going to disappear. So you would want to move back and forth, and so you want to find a position at which the image of the 6 LEDs from your flashlight is the sharpest. So I'm going to dim the light in the room and also zoom in my camera so that you can clearly see the image here on the back screen. Now that I zoomed in my camera, and now I'm going to start moving the lens holder with the lens again, you can see here how this mirror image here gets blurred if I move the lens closer to the screen, and if I move it farther away, you can find a sweet spot at which the mirror image is the sharpest. So that's gonna be somewhere, let's see, right here. So when you find the position of the lens at which the mirror image here appears the sharpest and very clear, at that point you would want to measure the distance from the back screen to the position of your lens. As you can see, I'm reading exactly 7 centimeters. So measuring from the back of the screen all the way to the position where the lens is about 7 centimeters. So we can conclude that The focal length of this biconcave lens is about 7 centimeters. In this part of the lab, you would want to trace the light rays coming out of your flashlight, going to the biconvex lens, and then hitting the focal point. So, in a sense, what you performed in a lab environment is what you're going to repeat here on a sheet of paper. So, as you can see here on the left-hand side, we have a flashlight. We have here 5 light rays that are moving in a parallel direction. And then here we have our biconvex lens with 2 focal points, one in front and one in the back. So what you want to do here is you would want to trace the light rays that are coming from the left-hand side, hitting the lens and then moving to the focal point. So the sketch that you're going to create here is going to be the replica of the experiment you performed in a lab environment in which you positioned the back screen at the focal point and measure the focal length away from the lens. In this second part of the sketch exercise, you want to sketch the case in which the back screen has been moved away from the focal point. In other words, the distance between the lens and the screen is more than the focal length. So in such a case, you would also want to create the sketch in which light rays are moving in the parallel, hitting the lens and then moving towards the focal point. However, your back screen is now being positioned away from the focal point. And then finally, the third case in our sketch exercise is the case in which the back screen is positioned closer to the lens than the focal length. So again, you're going to sketch the light rays moving out of the flashlight, hitting the lens and then moving towards the focal point. However, the back screen here is going to be positioned closer to the lens than the focal point. In other words, the distance from the back screen to the lens is going to be less than the focal length.